So we've said previously that one of the properties of electric charge is that electric charges can exert forces on other electric charges. If the charges are opposite in nature, then we know that this electrostatic force is attractive. Whereas if the charges are similar, okay, that is both being positive or both being negative, okay, then we know that the electrostatic force is repulsive in nature. In this slide, we'll talk briefly about the size of the electrostatic force. Okay, and in particular, compare it to a force that we're far more familiar with. Okay, that is the force of gravity. So let's make this a little more real by looking at a specific example. Okay, suppose I were to give you two paper clips, okay, each having a mass of about 1 gram, and I ask you to hold one of these paper clips, okay, hold these paper clips one in each hand about 0.5 meters apart, okay, about half a meter apart. Okay, this is roughly the separation distance that you would get by holding them with your arms extended straight out in front of you. So we know that there's a gravitational attraction between these 1 gram paper clips due to their mass. Okay, how big do you think the force of gravity would be? Well, it turns out that if you use Newton's law of universal gravitation and did the calculation, okay, for two 1 gram objects separated by a distance of 0.5 meters, you would find out that the force of gravity between these objects would be quite small, okay, on the order of about 10 to the negative 17 newtons, okay, far too small to actually measure. Okay, now I want you to imagine that the 1 gram paper clip in your left hand suddenly becomes a gram of pure protons, and that the paper clip in your right hand, okay, were to suddenly become a gram of, okay, pure electrons. Okay, note that they would still attract each other, right? Because they are opposite in charge. Okay, but now how big do you think that this resulting force of attraction would be? Well, to give you an idea of just how big, okay, the force of attraction would be between 1 gram of protons and 1 gram of electrons separated by a distance of half a meter, okay, I'll give you this comparison. You would have an easier time lifting an object as heavy as the moon on the surface of the earth. In other words, okay, it would be easier for you to, on the surface of the earth, lift an object as heavy as the moon as it would be for you to keep 1 gram of protons separated from 1 gram of electrons by half a meter. This electrostatic force is 10 to the 39 power times stronger than the gravitational force. And that difference is not just huge, it's confounded physicists, okay, for generations. Why should there be such a profound difference in the strength of these two fundamental forces? We'll take a look at one more example that I think nicely illustrates the profound difference in the size of the electrostatic force when compared to the gravitational force. This is an example I'm stealing from the physicist Brian Greene in his book on string theory. Let's imagine that you were to jump off of the Empire State Building. Let's take a look at, okay, the forces acting upon you during your journey. Well, while in free fall, you have every particle in the earth exerting a downward attractive force on you, essentially pulling you towards the center of the earth. Clearly, this is a noticeable force, causing you to increase your speed to accelerate at about 10 meters per second, okay, for every second of free fall. Okay, but then let me ask, if every particle in the earth is pulling you towards its center, then why don't you end up at the center of the earth? Okay, well, because it takes only a fine layer of atoms in the pavement that you hit, Okay, really the electrons in those atoms that are repelling the electrons in the atoms in your body, okay, to overcome this attraction of every particle in the earth, okay, every particle in the earth pulling you downwards towards its center. Okay, the electrostatic force from just a small number of electrons in the atoms at just the top surface of the pavement can provide a greater upward force on you than the force of every single particle in the earth pulling you downwards. This is possible only because, okay, the electromagnetic force is so many orders of magnitude bigger than the force of gravity. So what we just learned in the previous slides begs the following question. If the electrostatic force is so huge, then how come we're typically not aware of it? And if the force of gravity is so weak, okay, how come we typically are aware of it? Okay, it seems like a contradiction here. Well, it turns out that the force of gravity is noticeable because mass comes in only one type. Okay, thus, the force of gravity is always attractive, okay, which means that forces are additive. There's no cancellation. When it comes to charge, however, charge comes in two types. Okay, and forces due to opposite charges tend to cancel each other out, so the net force is zero. Remember that force is a vector quantity. To make this a little more real, let's take a look at an example of, let's say, some macroscopic objects. First, we'll take a look at the case of charge. Now, most macroscopic objects are electrically neutral. Okay, that means that they contain about as many positive charges, about as many protons as they do electrons. So let's suppose that I bring in a sample of matter here, and I'm showing you some of the charges. The red charges are positive, the blue charges are negative. And we see here in this sample of matter, of course, I'm exaggerating it, drawing it a little bigger just for effect. And let's suppose I bring in a charged object, okay, this red charge, big Q. So you'll notice that the sample of matter I'm showing you on the bottom is roughly electrically neutral. We've got as many positive charges as negative charges, yet, okay, when we bring in this charged object Q, let's take a look at the net force on that charged object Q. Now, hopefully you would agree that the protons in the sample of matter, that is the positive charges, okay, all of the little red plus Q's in our neutral sample of matter, those are going to exert a repulsive force on our charged object, okay, and as I'm showing you with the red force arrows here, whereas all of the blue particles that are negatively charged, those particles should exert an attractive force on our object. So you see here what the net effect is, okay, that because we have about as many positive charges as negative charges, we have about as many forces in one direction as the other. And since force is a vector quantity, okay, then these forces will cancel out. Okay, so the net force is roughly zero. Macroscopic objects cannot be massively neutral, however, since there's only one kind of mass. That is, every particle with mass attracts every other particle. Let's go through a similar argument, looking at a sample of matter. We'll focus here on the mass of these particles in the matter here. And let's bring in another object, okay, with mass big M. And you will notice here, when it comes to gravity, okay, all of those little particles in our sample of matter, and I'm counting 9 of them here, are going to exert an attractive force on this other sample of matter, okay, having a mass big M. Okay, and this is because the force of gravity, as we said, is always attractive. Notice that in this case, there is no cancellation of forces, okay, in which case there is a net force on that object. Okay, there is a noticeable net force. So even though the size of these forces, each of these forces may be very small because gravitational force is very weak, okay, the forces are additive. So cumulatively, there is a big effect. That is why, the force that you experience due to gravity around other objects near you is not noticeable. Yet, when you look at an object the size of the Earth, and you look at every single particle in the Earth exerting a force on you, okay, well, because the force is always additive and is always downwards, then that builds up to a noticeable force. All you have to do is jump up, and you will clearly feel the consequence of every particle in the Earth exerting that tiny downward force upon you. Okay, that even though the force due to each particle in the Earth may be small, it is always additive, and the net effect or net force is very noticeable. It is precisely because the electromagnetic force is so strong that we don't find many separated charges naturally occurring in nature. Okay, that is why most objects that we find are electrically neutral. So we now know that the electrostatic force is big, but how big? How do we calculate it? Well, we can thank Monsieur Charles Augustin de Coulomb, a French scientist who in 1785 stated his famous law that allows us to calculate the size of the electrostatic force between charged objects. So that's what we're going to take a look at in this slide. We start out by assuming that we have two charged objects. These objects have a net charge Q1 and Q2. Okay, so here are our two charged objects Q1 and Q2 separated by a distance R. We further assume that the separation distance R is much greater than the dimensions of the objects themselves. Typically, we consider these objects to be point particles. And we further assume that the charges are stationary when calculating this force. So given that, okay, according to Coulomb, the magnitude of the electrostatic force between these charged objects, okay, is given by this expression. Okay, K sub E, that is Coulomb's constant. We'll talk about more about that in a second. So the force is equal to Coulomb's constant times the product of the net charge on each object, okay, magnitude only, okay, divided by the separation distance squared. So we see here that just as in Newton's law of universal gravitation, where we had an inverse square law, Coulomb's law is another example of an inverse square law. Okay, the force gets weaker as the square of the separation distance. Let's talk a little more about the Coulomb constant, K or K sub E. You'll notice here the Coulomb's constant in comparison to the universal gravitation constant is quite large, right? About 9 times 10 to the 9th Newton meters squared per Coulomb squared. In this slide, I am going to introduce another related constant to the Coulomb constant. This is what we call the permittivity of free space, and we symbolize it with an epsilon naught. And you should understand that this is another constant that we will use in this course. This is in a Gaussian unit system, so we will be coming across this. And you see here that it is related to the Coulomb constant, right? Okay, this permittivity of free space epsilon naught is, equal to 1 over 4 pi times the Coulomb constant, and vice versa. So given one of these constants, you can go from one to the other knowing this relationship. So in this slide, we will gain some experience applying Coulomb's law and quantitatively confirm what we have stated previously about the relative size of the electrostatic force in comparison to the gravitational force. So in this example, we're told that the universe's simplest atom, okay, is that of hydrogen. And the simplest isotope of hydrogen consists of 1 proton in the nucleus and 1 electron at an average distance, of 5.2 times 10 to the minus 11 meters from the nucleus. A proton has a mass that's given, Well, we're also given the mass of the electron here as well. First, we're asked to calculate the gravitational force between these subatomic particles. So given their masses, knowing the universal gravitation constant as well as Newton's law of universal gravitation, we can quickly calculate the force of gravity between the electron and the proton, okay, for the hydrogen atom. So we plug in our numbers, we plug in the masses of each of these subatomic particles, the separation distance, don't forget to square it. And when we do the number crunching, we come out with this very tiny force, certainly too small to measure, about 3.8 times 10 to the minus 47 newtons. Now, in part B of this problem, we're now going to use Coulomb's law to calculate the electrostatic force between these subatomic particles. So we have all the information we need. According to Coulomb's law, we need to multiply the Coulomb constant, okay, times the charge of each of these subatomic particles. Remember that the charge of the electron is what we call the fundamental unit of charge. It's the smallest unit of charge that exists in nature. We can't have a fraction of this fundamental unit. So it's the smallest unit. It also happens to be the charge of one proton. So we're going to take the charge of the electron multiplied by the charge of the proton, which means we're basically squaring them since they're the same. And again, dividing by the separation distance squared. When we do that, we come out with an electrostatic force that's not particularly big, okay, 0.5 times 10 to the minus 8 newtons, yet when you notice that compared to the gravitational force, okay, it is many orders of magnitude bigger. So to actually make this comparison, let's take the ratio of these two forces. And when we do that, when we take the ratio, that is the force of the electrostatic force divided by the gravitational force, now we see this number that we alluded to previously, okay, this 10 to the 39th power. Okay, the idea that the electrostatic force between these two charged objects is about 10 to the 39 times greater than the force of gravity between them. Very strange universe that we live in, okay, to have such a vast, a profound difference in the size of these forces. Let's now talk about the direction of the force between the charges, okay, using Coulomb's law. And in order to do so, we're going to introduce some new notation here. So notice here that we describe the force in terms of the subscripts 1 and 2, and we introduce this unit vector here, okay, R12 hat, which I will explain shortly. So starting with the case of like charges here, we've got our two charges Q1 and Q2. We will introduce this displacement vector, okay, which is directed from charge 1 to charge 2, whose magnitude is simply the distance between these two charges, really between their centers of mass. And like I say, the subscripts 1, 2 tell you that the order and in which way this displacement vector is directed. In the same way, the unit vector, R12 hat, is also directed from charge 1 towards charge 2, and the magnitude of this unit vector, like all unit vectors, is 1. So in this case here, we see that F sub 1, 2, okay, it is a force on charge 2 caused by Q1. In other words, F12 is the force that charge 1, Q1, exerts on charge 2. And as we said, this unit vector R12 hat is the unit vector that is directed from charge 1 towards charge 2. Now, I'll be honest here, the notation that I'm introducing here is different than the notation that's introduced in some of the texts, and it is different than the notation introduced in Giancoli. And the reason that I introduce this notation is that it allows the order of the subscripts for the force to exactly match the order of the subscripts on the unit vector. And I think that that is going to be easier to remember. Okay, what is different is that with this notation, okay, F sub 1, 2, that is a force on charge 2, not on charge 1, okay, which is
the change in the Giancoli notation here. So notice here that, as long as you remember that F sub 1, 2, that is the force that charge 1 exerts on charge 2. It's a force on charge 2. Okay, I think everything else will make more sense because, like I said, the order of the subscripts on the force will match the order of the subscripts on the unit vector. So I'm showing you here the case, okay, for like charges. We looked at what F sub 1, 2 looks like. Similarly, okay, F sub 2, 1, that is going to be the force that charge 2 exerts on charge 1. Okay, and for the case of like charges, you'll notice that these forces are opposite in direction. In the case of unlike charges, okay, let's look at that. Here's our charges Q1 and Q2. So one of them is positive, one is negative. In which case we know that there's an attractive force, okay, between these charges. Now, here's the thing. When you use Coulomb's law, you will notice here, okay, that one of these values for Q1 and Q2 will be negative. What that tells you then is that F sub 1, 2, okay, the force that charge 1 exerts on charge 2 is going to be equal to, okay, don't forget this negative sign, it will be in the opposite direction of R12 hat. Okay, remember R12 hat is to the right, but in the case of unlike charges, F sub 1, 2 will be directed to the left. So by putting in the signs of the charges, okay, then you will automatically have the direction spelled out for you, okay, with this notation. And lastly here, okay, we will say that Newton's third law is alive and well, okay, that F sub 1, 2 equals minus F sub 2, 1. In other words, the force that, okay, charge 1 exerts on charge 2 is exactly equal in magnitude, opposite in direction to the force, okay, that charge 2, okay, exerts on charge 1. All right, so in this example, we will get some practice applying Coulomb's law and see how this new notation can be used. So in this example, we're talking about the force between two charges, a 9.5 microcoulomb charge that is given, located in terms of these Cartesian coordinates x and y, and a negative 3.2 microcoulomb charge located, okay, at a position, a different position in our coordinate plane. We want to find the force on the negative charge. So let's start by, okay, drawing pictures of these two charges here. Okay, we'll say charge Q1. Notice has coordinates 10 centimeters, 5 centimeters, and it is, okay, described by this position vector R1. Okay, charge Q2, the negative 3.2 microcoulomb charge, has coordinates 4 centimeters, 11 centimeters, and can be described, the coordinates can be described by this displacement or position vector R2. We want to find the force on the negative charge. So according to our force notation, let's draw in the forces here. Okay, first we will define this vector here. So remember, R sub 1, 2 is this position vector, displacement vector going from charge 1 to charge 2. Okay, and we will draw that in which case we can now say that F21, okay, remember that's the force that charge 2 exerts on charge 1, so it's a force on charge 1, and it's an attractive force, is in this direction. And likewise, F sub 1, 2, that's the force we're asked to find in the problem, okay, is a force that charge, okay, 1 exerts on charge 2, okay, and it is directed in this position, sorry, in this direction, okay, because these are unlike charges and the force is attractive. So, given this picture, let's apply Coulomb's law here. And we're going to start, okay, notice that this position or displacement vector R1 is given in terms of its Cartesian components. Likewise for this position or displacement vector R2, okay, which describes the position of charge 2 with respect to the origin. Okay, we can describe it in terms of its Cartesian components here. So the vector R12, okay, and think about what you know about vectors in the tail to tip rule, right? The vector R12 is simply R2 minus R1. Okay, and you will notice that, okay, when you take this vector r1 and you place the tail of this vector r12 at the tip of r1, okay, r1 plus r12 is equal to r2, or said another way, okay, r12 is equal to r2 minus r1. So it follows everything you know about the tail to tip rule of vector addition. And when we do the number crunching, we find out that, okay, this displacement vector can be described in terms of its Cartesian components as minus 6i plus 6j. The magnitude of R12, that is the distance between these two charges, okay, we get by using the Pythagorean theorem, okay, by taking the square root of the sum of the squares of these Cartesian components. Okay, and when we do the number crunching, we find out that the distance between these charges is 8.5 centimeters. Now we need to know that in order to determine this unit vector r12 hat. Okay, the unit vector r12 hat, okay, is what we get by taking our displacement vector r12 and dividing by the magnitude of the displacement, right? So we're basically taking the vector with the direction, okay, sorry, taking the vector with the magnitude and the direction, we're dividing by the magnitude, okay? So when we do that, we always get a magnitude of 1, but the direction will be left in place. So when we take this vector minus 6i plus 6j and divide by, okay, the magnitude of r12, okay, this is our unit vector here, okay, minus 0.71i hat plus 0.71j hat. And to convince yourself that the magnitude of any unit vector is 1, you know, take that unit vector, dot it into itself, essentially squaring it, and then take the square root, and you will find that you get an answer of 1. In other words, okay, you know, 0.71 squared plus 0.71 squared, find that sum and take the square root, and you will get a value of 1, as you do for any unit vector. So now that we have this, we're in a position we know everything we need to plug directly into Coulomb's law. So this is our expression for Coulomb's law. F sub 1, 2, that is the force, okay, that charge 1 exerts on charge 2. That's the force we're asked to find in this problem. It's equal to Coulomb's constant times Q1 times Q2 divided by R12 squared times this unit vector R12 hat. Okay, notice we plug in the value of Coulomb's constant here. Okay, the value of each of these charges, don't forget that, okay, Q2 is a negative charge, so you've got to put that negative sign in so that we get the correct direction here. Notice that R12 squared, we found the magnitude of R12 was 8.5 centimeters. That's the distance between these charges. We'll convert that to meters, 0.085 meters, and then we will multiply by our unit vector, R12 hat, which we wrote in terms of its Cartesian components. And when we do the number crunching here, okay, this is what you will come up with for an answer, that this force can be described, okay, as 27 newtons, okay, times I hat minus 27 newtons times J hat. So it's important that you understand how to use this notation, okay, how to find the distance between two charges given their coordinates, and how to be able to describe that unit vector R12 hat. In this slide, we will compare and contrast Newton's law of universal gravitation with Coulomb's law. And I think it's important to see that there are some really striking similarities between these two laws, but there are also some striking or glaring differences, okay, which, as we said in the opening slide, has prevented the unification of these forces. So, okay, in the case of what is it that causes the force of gravity? Well, basically mass. What is it that causes this electrostatic or Coulomb force? Well, we know it's this property we call electric charge. Assumptions we make here, okay, when you consider two objects with mass separated by a distance r, let's say having a mass m1 and m2, okay, when we talk about Coulomb's law, it's a very similar situation. We're comparing or considering two charged objects with charges Q1 and Q2 separated by a distance r. In which case, we can describe the magnitude of the force. Okay, it looks very similar from one law to the other. In the case of gravity, okay, it's directly proportional. The force of gravity is proportional to this proportionality constant, big G, times the product of the masses, okay, and inversely proportional to the square of the distance between these objects. And it is the same form of the law that applies to Coulomb's law, right? That electrostatic force is equal to a proportionality constant, is directly proportional to the charges, okay, of each of the two objects, and inversely proportional to the square of the separation distance between these two objects. So this striking similarity here, obviously tempts scientists, okay, and leads them on this path to say that there must be some way to unify these forces. When we look at the proportionality constant, now we get into some of the discrepancies. When you look at the force of gravity and that proportionality constant, as we've said, okay, it's extremely small. When you look at the Coulomb constant, however, it's very large in comparison. Okay, this tells us that gravity is a weak force, whereas the electrostatic force is a strong force. The direction of the force, okay, well, it acts along the line connecting the centers of these two objects in the case of gravity, and the same can be said for the case of charged objects. But now for the striking difference. Okay, in the case of gravity, okay, the force is always attractive. There is only one type of mass in the universe, so that all mass attracts all other mass. But in the case of charge, okay, we can say that the force can be either attractive or repulsive. Why? Because there's two types of charge in our universe. And this is a striking difference between gravity, okay, and the force that results from charged objects. So it should come as no surprise to you that this principle of superposition that you learned in your course on wave theory, okay, Physics 102 perhaps, is alive and well, okay, when it comes to forces. So we're saying here that for a system consisting of more than two charges, okay, the net force on any given charge is simply the superposition or vector sum, okay, of the forces due to each of the other charges. In other words, the force on charge 1 would be equal to the force, okay, that charge 2 exerts on charge 1, that plus the force that charge 3 exerts on charge 1, okay, and so on. So we use this, okay, in conjunction with what we know about vector addition, okay, to be able to find the net force on any given charged object. So let's get some practice applying this principle of superposition, some practice applying Coulomb's law as well. And this will give you some practice applying the component method of vector addition. It may have been a little while since you've done this, okay, but very important, when we talk about adding forces, and we'll see in the next unit adding electric field vectors as well. This problem involves 4 raindrops, okay, and as we learned earlier today, the charging of individual raindrops is ultimately responsible for the electrical activity of a thunderstorm. So we're going to take a look at 4 very special raindrops here. It looks like we got a silly one, okay, a happy one, a cool one, and each of these raindrops here has a charge. The charge is given. Notice that raindrop 1 here, given by charge Q1, is negative. Okay, raindrop 2 is positively charged. Raindrop 3 is negatively charged. Raindrop 4 is positively charged. So we're asked to find the magnitude and direction of the force on raindrop 1 due to the other 3 raindrops. So we will start, okay, let's just sketch in these vectors and apply Coulomb's law. So here we have F sub 2(1) using our force notation. This is the force that raindrop 2 exerts on raindrop 1. Notice that the force is attractive because they are oppositely charged raindrops. And we can find the magnitude of that force using Coulomb's law. All right, the distances are given to us in the problem. So when we plug in our charges, make sure the raindrops are expressed in, their charges are expressed in nanocoulombs. Okay, make sure to pay attention to those metric prefixes. The distance, the separation distance is centimeters, so we've got to get these into MKS units here. And we come up with a force of 2.8 times 10 to the minus 2 newtons. We will do the same for raindrops 3 and raindrops 4 as well. So for raindrop 3, notice that the force it exerts on raindrop 1, okay, is repulsive because they're both negatively charged. Once again, we can apply Coulomb's law to find the magnitude of this force. And then finally, for raindrop 4, okay, the force it exerts on raindrop 1 is attractive, okay, F sub 4(1). And we can, once again, apply Coulomb's law to find the magnitude of that force. So basically, we need to, according to the law of superposition, add these three force vectors. Okay, that is F21 plus F31 plus F41. And we can do this using the component method of vector addition. Since we're simply adding these forces, okay, we can resolve them into their respective x and y components. F sub 2(1), you'll notice, is directed exclusively in the y direction. It has no x component, okay, and its y component using our green coordinate system here is negative. When we look at F sub 3(1), we see, well, it's got both an x and a y component, so we're going to have to figure out what that angle theta is, and we can do that using a little right triangle trigonometry. Okay, we find out that there's a 51-degree angle there, in which case, okay, F sub 3(1), the x component, which is negative, is expressed by taking the magnitude of F31 times the sine of that angle, and the y component is positive, so okay, taking the magnitude of F sub 3(1) times, okay, the okay, cosine of, okay, this angle here, you will notice that the angle that I chose to find here, okay, theta, requires that we specify the x component as a sine and the y component as a cosine. Had I found this other angle here, phi, okay, then we could have expressed the x component as a cosine, the y component as a sine. It doesn't matter. All I'm saying is just be careful. You know, in physics, you cannot always assume that x is cosine and y is sine, like you do when you use your unit circle in a trigonometry class. And finally, okay, F sub 4(1), okay, we see that it is a vector that is exclusively in the x direction. Okay, and so it has an x component, okay, given by this. It has no y component here. So according to, okay, this component method of vector addition, once we've resolved all of our force vectors into their respective x and y components, we can separately add the x components from the y components. So when we add all of our x components here, this gives us, okay, the net force in the x direction. This is the x component of our resultant. Likewise, we add up all the y components. Okay, that turns out to be negative. That gives us the y component of our resultant force vector. I'm going to draw in these two components on my diagram here. Okay, so it looks like the x component, which I'm showing you here in black. Okay, and the y component, which I'm showing you here. And given those two components, we know then that our resultant vector is just the vector sum of those two components, okay, which I'm going to draw here as this pink vector here. So to be able to describe that pink vector, that force vector, our net force, we need to specify its magnitude and its direction. So its magnitude, well, we'll need to, for its direction, we will need to find that angle phi. Okay. The magnitude is, okay, we can get by using the Pythagorean theorem, right? The magnitude of the resultant is simply the square root of the sum of the squares of the components. So we'll take our x and y components for, okay, our resultant force, square them individually, add them, and then take the square root. That's just the Pythagorean theorem. And we come out with a magnitude of 3.3 times 10 to the minus 2 newtons. Okay, the direction here, we need to specify some angle. To specify that angle phi here, we can do that by taking the inverse tangent, okay, of the x component over the y component. And when we do that, we come up with an angle of 38 degrees. So that angle is the best way to be able to specify the direction, okay, of that resultant vector.